Hi, this is a follow-up video on the video about magnets, electromagnets, and inductors. And I found that I really have to cover capacitors and inductors together because they are analogous in many ways. The capacitor is fairly well understood. But I find that a lot of people don't really understand inductors all that well. So I'm using capacitors to help explain inductors. But we'll still see later that inductors are a very strange animal. Well, I've put two equations on the board. Well, there's four equations, but these are the most important ones that we'll talk about. Now, if you don't know calculus, don't worry about it. We're going to simplify these here in a few seconds. Now, this is an equation that relates voltage and current in a capacitor. This equation, you can see it's the same form. It also relates voltage and current in an inductor. But notice that the current and voltage are interchanged in these two equations. So they're the same form and they're kind of analogous, but voltage and current has been interchanged. Now these small symbols mean instantaneous voltage and instantaneous current. And we can greatly simplify things by talking about DC voltage and current. And to do that, we'll enter the world of LC Wonderland, I call it. Okay, here we are in LC Wonderland. I call it that based on something you'll see here in a few seconds. But this equation here becomes this when we put in the normal electrical units. Farad is the unit for capacitance. Of course, amps is the unit for current, and volts is the unit for voltage. This equation becomes this, and the unit of inductance is henries. So we can simplify this to these equations. V equals A times time in seconds divided by farads. And here amps equals volt seconds divided by henries. Now, if you do know calculus, you really have to pay attention or you'll get lost in simplicity. Okay, here we are in LC Wonderland, except I spelled wonder wrong. That's one, wonder. We're going to work with 1 amp and 1 volt for 1 second, 1 farad, and 1 coulomb. Everything here is 1. That's why I call it Wonderland. So this equation tells us that the voltage across a capacitor depends on the current times the time that was applied to it divided by the farads of the capacitor. So here we have a little circuit which is a constant current source with a normally closed switch. At time 0, we'll open the switch and let current flow into the capacitor. In 1 second, we'll reclose the switch and the current again will circulate through the switch, and the diode will keep the voltage on the capacitor. So we apply, for a time period of 1 second, we apply 1 amp to the capacitor. And this equation tells us that the voltage will do this. It will linearly ramp up to 1 volt. Now the energy that we're putting into that capacitor is an important issue, and energy is given in joules, which uses a symbol J, and joules are watt seconds. 1 watt for 1 second is 1 joule. Now a watt is a volt times an amp. 1 watt is 1 volt times 1 amp. Now, during this ramp-up period, the average voltage is a half a volt. So the watts that we're putting in here during this 1 second time period is 1/2 of a volt times an amp times a second. So let's change this symbol back to C. The C is equal to 1 farad still. Okay, let's solve that equation for amps. So amps equals volts times the capacitance divided by the time in seconds. And now let's take that value for A and put it into that equation. So now we have energy equals 1/2 volt. Now this is what this amps is. So that's times volts times capacitance. We have a times seconds over there, and then we have this divided by seconds. So energy is equal to 1/2 CV squared. And you may have seen that equation before. Okay, we just derived the equation for energy stored in a capacitor. And the question might come to mind, where is the energy stored? How is it stored? And the typical line is, well, it's in the charge that you put on the capacitor. Well, the units of charge are amp seconds, and the units of energy are volt amp seconds. So there's more to this than meets the eye. The energy is really the charge, but the voltage at which the charge resides. If I have a coulomb at 1 volt, that's a certain amount of energy. If I have a coulomb at 10 volts, that's a lot more energy. So it isn't just the charge, the coulombs, that determine the energy, but also the voltage at which those coulombs reside. So this equation will give you the numerical value of the energy, but it tells you nothing about what's really going on. And sometimes too much reliance on the math will give you fuzzy ideas about things. Okay, let's calculate how much energy we have put into the capacitor in our example. The capacitance is 1 farad, so we have 1/2 times 1, and the voltage is 1 volt, so we have 1 squared. So this equals 1/2 joule. So a joule is a watt second, so this says we can deliver 1/2 watt for 1 second, or 1 watt for 1/2 a second. Now what if we change the capacitor to 1/10 of a farad? This equation tells us we'll end up at 10 volts. And I'm out of room here, so now let's calculate the energy after putting 1 coulomb. Remember, a coulomb is an amp for a second into a 1/10 farad capacitor. So that energy is 1/2, and we're using this equation here. 1/2 of the capacitor, which is 1/10 of a farad, times the voltage squared, so that's 10 squared. So now, if you go through that, you'll end up with 5 joules. So that means we can deliver 5 watts for a second, or 1 watt for 10 seconds. So here we see how the same amount of charge can give us different amounts of energy depending on the voltage that the charge is at. So that's the point I'm trying to make here. So next, let's look at inductors through the same method, and we'll stay in what I call LC Wonderland and go through inductors next. Okay, here we are in LC Wonderland, and we're going to be talking about inductors. Now we're going to be dealing with 1 Henry and 1 volt and 1 amp, etc., like we did for the capacitor. So in case you're not familiar with inductors, inductors are given in henries or microhenries, millihenries, etc. And there's another term here we got to cover briefly, and that's the unit Weber. Weber is the amount of flux, magnetic flux that's generated when you pass a current through an inductor. And in the first video, I show you how to map the flux going through a coil of wire with current passing through it. So the Weber is the amount of flux generated by an inductor. Now there's another term that I'm not going to get into. It's called the Tesla. And the Tesla is Webers per square meter, which is flux density. Now, a lot of discussion about magnetics will try and get you into flux density right away. And that ends up sidestepping a lot of issues that really need to be understood before you get into flux density. So at any rate, when you pass current through an inductor, you generate flux that's measured in Webers, And from a mathematics standpoint, that's usually given the symbol, the Greek symbol phi. So phi shows up in a lot of equations. So now we're going to do with an inductor just like we did with the capacitor, except voltage and current are interchanged here. And with our little circuit, we're going to apply a voltage to the inductor. And here we need a diode to provide a path for the current when we open our switch. So what we're going to do is close that switch at time equals 0, and that'll apply 1 volt to our 1 Henry inductor. At the end of that period, we'll open the switch to remove the voltage. Now during that time period, our base equation that we started with says that the current is going to ramp up to 1 amp if we have 1 Henry and 1 volt for 1 second. So it turns out a Weber of flux is equal to a volt second. Just like with the capacitor, the Coulomb was equal to an amp second. So it's all very similar, just some things interchanged. So let's talk about energy again. Here's the same equations we had before. Energy's measured in joules. A joule is a watt second, and a watt is a volt amp. So a joule is a volt amp for a second. And in our particular case, we have 1 volt second times an average value of a half an amp. So our energy is a half an amp times a volt times a second. So these are both 1, the volt and the second. So if we solve this equation here for volts, we'll have volts equals amp. And let's change our Henry to L, the inductance. So the volt equals our amp henries per second. Okay, we've solved for V. Now let's take this expression for V and plug it into that equation. And we have energy equals 1/2 the current amps times this, which is amps times henries over seconds, and that's all times seconds. So the seconds cancel out, and we have E equals 1/2 L times the amps squared. And you'll usually see that as 1/2 Li squared when we get back to the symbol I for current. So if we change to well, just like with the capacitor, when everything is 1, we end up at a half a joule. If we go to 1/10 of a Henry, from this equation it tells us we're going to end up at 10 amps. And when we put that into the equation, just like with the 1/10 of a farad capacitor, we end up at 5 joules. Okay, so using the same volt seconds, which will end up giving us the same amount of flux, not flux density, just total flux. The Weber of flux is a volt for a second. So for the smaller inductor, that flux is at a higher current. So it's not just the energy is not just stored in the flux. It depends also on the current at which the current that's generating that flux. So again, the energy is not in the flux totally. It's a function of the flux and the current that's generating the flux. So that's basically what I wanted to show here. By the way, this diode here is sometimes called a back rectifier or a back diode. And what it does is allow the current in the inductor that was flowing this way originally. When we open the switch, the current can flow through that diode. So the energy is not in the flux. In a capacitor, the energy is not in the charge. It's a function of, in this case, flux and current, and in a capacitor, the charge and the voltage. So I hope this oversimplification makes it more understandable than just using all the typical mathematical symbols. Okay, we're back in reality now. And one of the things that makes capacitors fairly easy to understand and work with is that very, very good capacitors are available. In fact, you can make a very good capacitor yourself using aluminum foil and cling wrap. And it'll hold charge for long periods of time. You probably can't make it as small as a commercial capacitor, but you can make a very good capacitor. But you can't make a very good inductor. And the reason for that is inductors have resistance. That's the internal resistance. It's the resistance of the wire that the inductor is made out of. And because of that resistance, current won't stay where you put it. The current always wants to decay. This just makes inductors strange compared to capacitors. You can put a voltage on a capacitor and it'll stay there for a long, long time. But you can't put a current in an inductor and make it stay there. So if somehow I had 10 amps flowing through that inductor and could short out the terminals so that that current could continue to flow, it would decay due to the resistance of the inductor. Now, in most capacitor circuits, we intentionally, there's the capacitor, we intentionally put a resistor here in the circuit for the current, for the voltage to decay, and we get the typical time constant decay of voltage. So it's primarily this resistance that makes inductors kind of a hard thing to work with. It's a thing you can't just hold in your hand with current going around like you can with a capacitor. You can hold it in your hand with voltage applied to it. I don't mean connected to it, but voltage there because of the charge within the capacitor. Well, this video is getting pretty long and I have a lot more to show you. relative to inductors. So subscribe so you don't miss the next video. Thanks for watching.